So this time, what have we got? We've got a pool table. I just stole one off the internet. Struck from a spot 100 millimeters from cushion A. So we've got cushion A here, and cushion B here. So these, I don't know what these fellas at the end, they're usually called cushions, I think. And so it struck so the pool ball struck from a spot 100 millimeters from cushion A. So this is where the pool ball starts. So it starts here, like so, and it's 100 millimeters from A. I'm going to change everything to meters because my speed's given in meters per second. Could change these to millimeters per second, wouldn't really matter. Anyway, it's 0.1 from there. We know the total length of the table is 2.24 meters, 2240 millimeters. So therefore, we're just being careful about this. The total length, so we're going to take the starting point as 0 displacement. So, because it asks us what's the displacement of the pool ball after 3 seconds. If it doesn't tell us relative to what, just assume it's the starting point. Relative to the starting point is the displacement you're looking for. So it's going to start here. So that's going to be minus 0.1 if I take positive displacement in this direction. Don't have to, could take positive displacement in the other direction. But anyway, I've taken it this way. So therefore, the displacement when it hits this other cushion, well, the total distance between this point and this point is 2240. That's at minus 0.1. So this must be 2.14 meters. Okay, because you've got that. You're not starting from 0 here, you're starting from minus 0.1. So this here must be 2.14 meters. Okay, so just be careful to think through exactly what everything is. Then what's happening? I shouldn't have let go of that. We'll see how we go. So what's going to happen here is it struck 100 millimeters from cushion A, and it's traveling towards cushion B. So this thing is traveling like this. So it goes down here like that, travels along, hits this and bounces back. And for this kind of pool table, that change in velocity is almost instantaneous. That's why we're not worrying. Actually, it'll slow down and then accelerate in the opposite direction. We're not worrying about that. We're just thinking about it as two different velocities. With zero acceleration or constant velocity during the main stages, and we're just assuming that this turnaround is almost instantaneous. Now, there's another thing we're doing with this question, just thinking this through. So it's going to travel along here at 1.5 meters per second. Sorry, it's hard for me to do this constantly. Then it's going to bounce, then it's going to come back a little bit slower because it's lost a bit of energy when it bounced. So at 1.25 meters per second, it's going to come back again. Going to keep going until it hits this, and then it would bounce back again. Where it's not in part of the question. We'll slow down some more, and it would keep bouncing backwards and forwards till it eventually stopped. We're assuming that as it's traveling, it's not losing speed, so it's got constant velocity, and we're also ignoring the diameter of the ball in this question. Just thinking about that, because we're going to say it's traveling 2.14 meters. It won't quite travel that far because the center of the ball won't get to the cushion. It's just the edge of the ball will get to the cushion. So we're kind of ignoring the diameter of the ball as well in this question. And if you do that in a question, you just have to state that you did so. Now, and it's reasonable because the diameter of the ball is pretty small compared to the overall length of the table. So what do we have to do? It's the opposite cushion bounds, blah, blah, blah. What's the displacement of the pool ball after 3 seconds? So what we're going to have here is, in the examples we've looked at so far, they've just had one stage, like nothing is changing velocity or anything like that. In this case here, what's going to happen is it's going to travel until it hits here, and then it's going to bounce back again. So what's the displacement? So we're going to have to do this in 2 stages. We're going to have to figure out how long it's going to take for the ball to get to this point and bounce back. So how long it's going to take to get to this point, and then we're going to have to figure out how far it'll travel after bouncing in the remaining time. And then the displacement is just going to be basically the position. So it's the displacement is just a position relative to O, and that's what the displacement's going to be. How far is the pool ball traveled? And so let me just show you that. So maybe after a certain amount of time, the ball's going to be here. I've missed the outline of my ball. Just give me a minute. Oh, I'm going to get too messy. So let's just see if I can grab the whole thing this time. So it's going to bounce and maybe it's going to come back to here somewhere. The displacement, let me just draw it. So that was our starting point here. The displacement at time t is this distance. So the distance relative to O. But the distance travelled, so how far has the pool ball travelled? It's going to be this distance to get all the way to here, and then plus this distance to get back to here. So the two things are different. And displacement could be negative. In this case, I think it's going to be positive if it travels for 3 seconds. Could be wrong, actually. 0.5 meters per second. See what happens. So let me just get rid of that. So what we'll do first is figure out how long is this pool ball going to take to travel from this spot O to the cushion. So we're going to have to think about this in stages. Let's figure that out first. So this is really part of part A. So part A. So first we're going to calculate time to hit cushion B. I wonder if it would be more sensible to put this as 0. I'm going to keep the whole length. Might have been. I think I might do that actually. I'm just going to change this. I don't think it won't matter. You could do it either way, but I'm just thinking it might just be a bit tidier if I just put that as 0. This here is 100 millimeters. So let's say 0.1 of a meter. We'll keep everything in the meters, 0.1 meters. And this point here is 2.24 meters. So what do we know? We know, so we're trying to find the time. So we know the position at time t is just equal to starting position plus, for constant velocity, it's just the velocity times time. So in this case, for the ball, it's starting at position 0.1, so it's starting 100 millimeters from A. So let's just put that as 0.1 as its starting position, plus V naught for this part of the travel was 1.5 meters per second. So it's 1.5 meters per second times time. And we want to find out the time at which it hits the other side. So that is going to equal 2.24. So that means we are going to get 1.5 t is equal to 2.24, take away 0.1, just rearranging this. So t is equal to 2.14 divided by 1.5, which is equal to 1.427 seconds. So it's going to take 1.427 seconds to here. So the remaining time we have, so let's just do this, after hits cushion B, time remaining is going to be equal to, so we're looking for the time at 3 seconds, I think, wasn't it? Yeah. So it's time remaining equals 3 seconds minus 1.427 seconds. I don't really know why I'm putting seconds in my equation here. As long as I'm thinking about it, it's fine. Which is going to be 1.573 maybe. Let's just check that. 3 minus 1.427, 1.573 seconds. So now what's happening? So we need a new equation for this because it's changed. So it's not, we've got a new stage of this motion. And so for this stage of the motion, we're starting at a displacement of 2.24 meters. It'll be interesting to see what happens here. See if it gets back to cushion A or not. So let's just see what happens. So for stage 2 of motion, let's say, the displacement at time t is equal to the starting position plus v naught times t. So in this case, for this second stage, the starting point for this stage is when it's at cushion B, so that is equal to 2.24 meters is the position. And it's heading back the way, so it's going negative 1.25 times t. And we want to figure out where's the ball after another 1.573 seconds has passed. So therefore, S at time t is going to be equal to 2.24 minus 1.25 times 1.573, which is equal to 2.24 minus 1.25 times 1.573 is equal to 0.273. 2738 meters. Now, that's fine. So it's ending up 0.2738, so it's here somewhere. There is a reason why I maybe shouldn't have changed those. That's okay. We'll get to that in a minute. So 0.2738 meters. And so if this had ended up being negative, you can imagine negative would be off here somewhere. It can't do that. It would bounce off this cushion and head back the other way again. And so if this had ended up being negative, I would have had to add another stage of motion. So I'd have had to figure out what time is it going to hit this cushion and how much time remains, and then calculate where it would have ended up after that time heading back the other way again. But because this is positive, that means it hasn't quite reached that cushion yet. It's here somewhere, 0.273 meters. And so that's all good. So now we have got to think about displacement. So this is why I was saying maybe I shouldn't have changed it back. So it's saying, what's the displacement of the pool ball after 3 seconds? And if we're talking about a displacement and it doesn't tell you from where, we assume it's relative to the starting point. And so displacement relative to A, cushion A, because that's where I've put my 0 for displacement, is equal to this value that we just calculated, 0.238. Displacement relative to the starting point, which is what the question's asking for if it doesn't state what the displacement should be relative to, is going to be equal to, well, it's going to be, the starting point was 0.1 meters from A, the ball's ended up 0.273 meters from A, so it's going to be 0.2738 minus 0.1, which is 0.174, say, meters. Okay, and so that's the answer to question A. Displacement from initial position of ball is 0.174 meters. Okay, that's the first part of this. What's the next part? How far did the pool ball travel after 3 seconds? So let's have a look at that now. So the distance traveled is just the total distance. So distance, so this is part B, distance traveled. So let's go back and think about what that pool ball did. So it traveled from here to here first, and so that was 2.24 meters minus 0.1 meters, and then it came back to here, which was at 0.2738, so 0.2738 from A, so that's going to be 2.24 take away 0.2738. You follow me? So it's got two paths. Let me just do a quick sketch to illustrate that. So what it did was, this is 2.24. This was 0. It started at 0.1 and it went like so. Hit the cushion at the other end. And then, it might be nicer just to do this underneath. We could show the two stages. So did that first. And then it went in the opposite direction. And finished at 0.2738. And so the total distance travelled is going to be equal to 2.24 minus 0.1 plus 2.24 minus 0.2738, which is equal to, now there's an interesting thing, I'm probably making a bit of a meal of this, 2.24 minus 0.1 plus 2.24 minus 0.2738. Now maybe is the way you need to do it. So it's total, it's travelled 4.11 meters. The pool ball travelled. Just checking that answer. 2.24 minus 0.1 plus 2.24 minus 0.2738. Yep. - 4.11 meters in total. Okay. Next. What does it want us to do next? So how long after being struck will the pool ball take to travel back to cushion A? I've got lots of B's here. I'll go back and fix that in a minute. So this should be A, B, C. So we're on to... Okay, so part C. How long after being struck will the pool ball take to hit cushion B? And so we've already calculated that. So time to hit cushion B is equal to, we calculated it here, it was 1.427 seconds, so 1.43. Let's see, for part D, it wants to know how long it'll be until it, from after being struck until it hits cushion A. So that's going to be, well, it's going to be time to hit cushion A is just going to be equal to, so it's going to be that 1.43 seconds to get to B. And then we're going to do, well, the distance it has to travel to get to cushion A is 2.24 meters. And after it hits cushion B, it's traveling at 1.25 meters per second. Said that in the question. So the time to get back to cushion A, I might just put this as 4 significant figures because we're reusing it. Just double check that's the right value. Yep. So it's going to be 1.427 plus 2.24 divided by 1.25. It's going to be 3.219 seconds. Now we could check that because we knew after 3 seconds it only had 0.2738 meters to go to get to the end. So let's just check that. If we do 0.2738 divided by the speed at this point is 1.25 is equal to 0.219. So we'll have to go for another 0.219 seconds. So that's a quick check and it looks okay. So let's just drag that across. Now it wants us to draw a diagram showing velocity, displacement and distance travelled by the pool ball at time t. So it's just looking for some graphs of this motion now. So what I'll do is I'll just underline my other answers first, and then we'll try and draw these graphs. And probably we'll just do this, I'll add this to the question later as well and fix the question, but we'll just do this for the first 3 seconds like it was talking about up here. So we've got this, and basically this is just drawing on together all the information we've got so far and making it into a little graph. So we're going to have 2 graphs. One of them is going to be of velocity. Well, we're going to have 3 graphs. One of them is going to be displacement, and one of them is going to be distance. So E. So let's go for velocity first. The maximum velocity we've got is 1.5, and then it is going to go negative. So let's just, don't want to do them too big. And remember, when you're drawing graphs, you need to use a ruler. So in the quiz 2, some people were drawing graphs without rulers. They didn't label their axes. They didn't put on some numbers to show the scale. So just need a bit of care on that stuff. So this is going to be, for the first one, we'll do velocity first, times time, and we're going to go a total of, so this, the maximum velocity is 1.5, so we'll go 1, 2, and this is in meters per second. And this is going to be -1, -2, and we have to go for 3 seconds. So we might go 1, 2, 3, just do that, 1, 2, 3 seconds, and then we'll just redraw this. Okay, so the ball started with a velocity of 1.5 meters per second, and we figured out that it hit cushion B after 1.43 seconds. So it's going to come along here, and then it's going to get to about 1.43. So let's just, so this is going to be 1.43. I'm not going to put the units, oh sorry, it's not, it's 1.5 meters per second. Is the velocity, and it's going to go until 1.43 seconds. Then it hits that cushion and bounces and goes in the opposite direction, so we're going to get a negative velocity for that. It's going in the opposite direction, so it's going to come down here and it goes at 1.25 meters per second, like so. And then it keeps going like that until it gets to the end. Let me just stick that 3 up at the top. Now, so that's 1.25. Might be, I'm unsure of whether you should put your units on these or not. I don't think it really matters, but you've got your units here, so you don't really need to put them here, but it can get a bit confusing about what's time and what's the velocity. So let me just put it on to show what it is, 1.5 meters per second, 1.25 meters per second. And it's negative, so we'll put it on as negative 1.25 meters per second, so that's cool. Do I want to shade it? You could. It's less usual to shade these types of diagrams, unlike shear force diagram and bending moment diagram, so I think we'll just leave it without hatching it, I mean. So for the next one, this is displacement now, so the symbol for displacement is S, and the maximum displacement will be 2.24 meters, and it never goes negative. So we're coming back up to this now. So basically, this was my displacement here. But I've got to take it relative. So it could go negative, it could go to -0.1. We should be taking it relative to this starting position because the question didn't tell us about that. And so really, I shouldn't have changed this to 0 and 2.24. I should have kept this as 0, but that's okay. Just have to be careful with that. So we could go, so we're going to have 0 here, so we could go positive 2.24 and we could go negative 0.1. So 1, 2, 3, 2.24, negative 1, maybe something like that. Time is just the same as it was last time. And this time we're talking about displacement here. Now, there's a bit of a trick, which is exactly the same trick as it was going from, for example, a line load to shear force, or for going from shear force to bending moment. And that is the area under the velocity time graph is going to be the displacement. So the area between any 2 points, allowing for positive and negatives, the area between any 2 points on the velocity time graph is going to be equal to the displacement at that point. So what we'd have is we're starting from displacement 0, and then it's going to go at 1.15 meters until it hits B. Now we already know what that is. It's going to be a displacement of 2.14. So let's put this 1, 2, 3. And so it's going to be about 2.14, which will be here somewhere. And so that's where it's going to get to at 1.43 seconds. And so it's going to be here. Now let's just check if this trick about the area works. So if that works, I should get 1.5 times 1.43, approximately it's rounded, times 1.43. So that's the area under here is equal to 2.14. So that's all good. Don't know why I drew my dot there. It's here, 2.214 out here. Okay, so just by thinking about it, it started at 0.1 and it went, the total length of the table is 2.24 meters, so it should be 2.14 meters as the displacement after 1.43 seconds. Or if you hadn't done all those calcs already, you could just figure out the area under this velocity time diagram. You can also think of it in terms of each second, you should be traveling 1.5 meters. And so if you were to do 1 second here, that's 1, 2, 3 seconds, then it should be a 1.5 at that point, because the area would be just this times 1. So there's a few different ways you can do it. Now, now the area is negative, so it's going to push my displacement in the negative direction. Still the area under this though, but we've already calculated all this, and we know that its final position after 3 seconds was and it's relative to the initial position of the ball, that's fine, was 0.174 meters. So this is 0.174, not for 0.2. So this here would be 2.14, always because it's relative to that starting point rather than relative to cushion A, and this would be 0.174, would be that there. And that's my displacement time graph. Okay, so it's just showing what's the displacement of this at time t. Now, the last thing it's asked us to graph, I won't usually ask you to graph this, I don't think, but it's just to show what the difference is between displacement and distance. Going to have to be quite a tall graph this time. So for the distance travelled, unlike displacement, which can go negative, because it's getting back closer to the point you started from, in the case of distance, that won't happen. Distance keeps increasing. So it doesn't matter which direction it's going in, it's still traveling further, if you know what I mean. And so we're going to start at 0 again, and it's going to start off the same. So let's just do 1, 2, 3, 4, and this is in meters. Displacement, usually distance. This is time in seconds, time in seconds, time in seconds. So it's going to start off the same. It's going to go to 2.14 after, and this here was 1.43 seconds, wasn't it? Something like that. So it's going to start off the same. It's going to get to 2.14 after 1.43 seconds. I don't know why. Okay, this should probably be, I haven't really drawn it very well. This should be a little bit more that way, I reckon. Maybe drawn it okay, I just haven't Put that on very well. Yeah, it's a bit better. I should really measure that with a ruler or something to get it in the right place. So it's going to start off the same, 2.14 after 1.43 seconds. So we're going to end up here. So this is 1, 2, 3 seconds. So it's going to start off pretty similar to what we had last time. It's going to be 1.43. Then the difference is going to be is it's going to keep going positive. So it's going to keep going. So the distance is still increasing. It's going in the other direction, but distance doesn't care about that. And so we did calculate previously the total distance travelled, 4.11 meters. 11 meters. So it's going to be after 3 seconds, it's going to be up at 4.11 meters, which is here. And you can see the slope is a bit lower because the speed is a bit lower. So it's got a lower slope. And so this here was 2.14 meters. This was 4.11 meters. I've already indicated that time. And so that's my distance time diagram. We could, okay, and that's that question done. So quite a lot to that question. And so we'll do some more on this type of drawing graphs for each stage. And this kind of motion where you can't use one equation to describe the whole thing. So where something changes partway through the motion, that's called erratic motion. And so we'll go on to cover that in a bit more detail as well.